Hi, it's time now to move to lecture 16 and see how we can apply everything we've learned so far to cases that actually that can be solved experimentally, that can be tackled experimentally. And this is where the introduction of thermodynamic potentials is very important. This is basically where all the chemistry and chemical engineering and other processes use those properties that we have learned so far. Because it turns out that the internal energy that we've discussed so far is not used much in thermodynamics, at least in practical thermodynamics, in terms of chemical reactions, for example. So what we know is that the internal energy is what physicists usually go to intuitively. This is the total energy of the system. So this is, we've seen it, there is a reminder in the blue box there that the second line simply tells you the first law of thermodynamics. The first line tells you that the internal energy is conserved in the sense that it's a state variable. U is a state variable, so any integral over a loop, whichever the loop is going to be equal to 0. And we also know that the component of the internal energy, Q and W, are not state variable. And this is translated mathematically by the third equation that says that the integral over a loop of dq is not equal to 0, and that's the reason why we use a special symbol for d. So it's not an exact differential, unlike u, for example. And finally, the last equation include both first and second law of thermodynamics, where we were able to write that du is equal to TdS minus PdV for a reversible process. So TdS is the reversible heat transferred, and minus PdV is the reversible work performed. But this equation still holds for any cases, since du is a state variable. Okay, so this is what we've done so far. So it turns out that, of course, mathematically now, we can certainly build a number of other state function, a function of state, because we have a number of them at our disposal. I mean, for example, U, T, S, P, and V are all function of state. And what we are going to do today in this screencast is to show how we can combine those different state functions and then build things that can be that are available experimentally. So this is a very important lecture, which is usually one where students say the math is too difficult, but I hopefully am going to tell you that the math is not really difficult. What's difficult is that there are many moving parts. So we'll get there when we get there by the end of this screencast. So we are going to introduce new functions of states. We're going to introduce the enthalpy, the Helmholtz free energy, and the Gibbs free energy. And I'm going to try to give you an intuition how we come up with those seemingly arbitrary functions that are described here on this slide. But I'm going to go one after another, and I think it should be pretty clear why they are introduced. But before we do that, let's go back to the internal energy, as I mentioned. So the first law of thermodynamics, as I mentioned just a second ago, is du equal TdS minus PV. And what's important from a mathematical standpoint is that this equation shows that variation in U can be calculated, can be obtained by considering variation in entropy and volume. So in other words, we say, when we see an equation like this, automatically you should be able to say that the entropy and the volume are the natural variable of the internal energy. In other words, U can be written as a function of S and V. Of course, we know that from that perspective, we can find a case of constant internal energy if the entropy and the volumes are fixed. This is come directly from the first equation. So that's all very interesting, and even further, we know what the prefactor T and minus P are from multivariable multivariable calculus, sorry, and these are given by this directly as expected. So I like to also remind you that it's very important to put the subscript V and S, because those partial derivatives depend on the constraint, and the constraint is actually labeled there on the subscript. So like the V is constant volume. Now, it turns out that this equation is very useful so long as the natural variables are also the variable that you can control experimentally. So that should already be kind of a red flag to you, because even though volume can be controlled experimentally fairly easily, I would say, entropy is certainly not. I mean, this is possible, of course, but if somebody comes to you and say, here are reactants for my chemical reaction, can you please perform this reaction at constant entropy? And this is where you're going to scratch your head, because you say, well, maybe the internal energy U is not really the relevant function of state that I should consider. And this is exactly what chemists say. So what's the reason why chemists do not use the internal energy? So they would like to use another function of state that depends on variable that can be controlled experimentally. So in other words, they want to have another function of state that will depend on other natural variables, like, for example, temperature or pressure. And this is what we are going to do today. For example, if we have a same volume case for the internal energy, we have Tu equal Tds. If it's reversible, I can replace ds by dq reversible divided by T. And therefore, in that case, if we have a constant volume, so isochoric is same volume. If we have same volume and reversible, then du equals Cv dt. And we've seen this before, right? We've discussed this before. We've seen this equation before for the ideal gas. So, for example, and of course you can integrate this and get the internal energy of your system, and this is fine, so long as we can have replaced by reversible process and so on and so forth. But in reality, we do not necessarily want those constraints. We want other constraints. Imagine somebody wants to keep the pressure constant. Well, the pressure constant is a very important constraint, because this is how most of the chemical reaction take place. Usually, if you remember your lab, your chemistry lab, both in high school or maybe first year in college, usually your beaker is open. That basically means that the pressure of the atmosphere is pushing on your experiment. That means the pressure is constant. Okay, so it's like a pressure reservoir, if you will. It doesn't matter how many molecules escape and so on, the pressure is still the same. So how do we keep the pressure constant? So what we want to do is to basically now move to the realm of mathematics and say, how can I find something that looks like internal energy, but it's modified so that my natural variable are going to be P, for example, instead of V, let's say. Well, let's say du equal Tds minus Pdv. If I were able to add PV, if I were able to add Pdv and subtract Vdp, that would be done, right? Okay. So how do you do that? Well, if you add PV to the internal energy, it looks to me like it's going to be the recipe to get rid of the PdV there. Let's try it. We're going to call this function the enthalpy, and we are going to see it's related to the heat of the reaction. But let's just keep doing this. So H equal to UPV, and of course, if I take the differential of H, I obtain TdS minus PdV plus VdP. And when I do that, I obtain automatically that the differential, and so as expected, we replace the natural variable, and the natural variable for the enthalpy H that we define this way have now become S and P. And this is interesting because now the variable that we can control is pressure and entropy. Of course, we still have the issue with entropy, but imagine that it's hard to control unless we have a reversible process, in which case it's related to the heat, right? We've discussed that at length when we introduce entropy. But what's interesting is that if you have an isobaric process, so same pressure, we find that dP is equal to 0. There is no variation in pressure. Therefore, dH is equal to TdS. So very much similar to what we did before. And then we find now, of course, that dH is equal to dQ reversible. Why do I do that? Because I can ds is defined as q reversible divided by t. So if I have a reversible isobaric process, I can do this. And because if it's isobaric, same pressure, the dq rev is Cp dt, right? The amount of heat that has to be transferred to change the temperature by 1 Kelvin is the heat capacity, it's Cp, at constant pressure here, of course, because it's an isobaric process. So we find that the heat that we release or we get in the system between temperature T1 and T2, can be positive or negative, is going to be given by this formula. And so what is very interesting is that this formula is almost the same as the one I had for du, for delta U from the previous slide, with two differences. One is that instead of Cp, of Cv we use for the internal energy, now we use Cp. And the second difference is that this formula, of course, is well, is appropriate for an isobaric process. So H, the enthalpy, basically change in enthalpy is going to give you the amount of heat that is transferred in or out of the system at constant pressure. So that's starting to be a little bit more practical if you do a chemical reaction, for example, but other processes at constant pressure. For example, everything that happens at constant pressure on the surface of Earth. So that's nice. We've already introduced a new function of state, the enthalpy, which is best choice for constant pressure. Now, you notice that by doing constant pressure and constant volume and this thing like this, we have access to the heat. But we do not have access to the work here. So really the focus is on heat. We get the heat at constant volume or the heat at constant pressure with the internal energy or the enthalpy respectively. So there is still work to do, of course, and it's not surprising since we have four variable of state, which are T, S, P, and V. So of course there are four possibilities to arrange them into the differential. So we are going to get there. But before we get there, I'd like to say a few words about the enthalpy. The enthalpy is, of course, the heat absorbed by the system. Absorbed, it can be positive or negative, of course, depending on how we do this. And so, as I said, the isobaric conditions are easy to obtain in experiment because we usually work at atmospheric pressure. And then that means that if we are able to keep both the entropy and the pressure constant, we have constant enthalpy. And finally, if you remember the multivariable calculus that with H depending on S and P, the partial derivative of H with respect to S and with respect to P with the proper constraint are going to give me the prefactor. So we have another definition of the temperature, which is now the partial derivative of the enthalpy with respect to entropy for constant pressure, and we actually have a definition of the volume, which is the derivative of the enthalpy with respect to pressure at constant enthalpy. And of course, T and V are kind of a function that change during the process, as you know, because T and V are not really those natural variable for the case of enthalpy. So you see, we are starting to get a lot of different definitions of our constant of variable of state, and some of them are difficult to calculate. Like, for example, how do you calculate the change in enthalpy when you change the entropy? And we are going to see how we do that later, because as you notice, we have so many equations coming from just four variables. So clearly, they must be connected to one another, especially because we have exact differentials. So all the theorem that you studied in multivariable calculus are going to come in handy to connect all these. And this is what we'll do before the end of this screencast. So we've done quite a bit of work. We've defined U. We have defined U since the beginning of this course. And with a lot of work, we found it was TdS minus PdV. And then we just defined H, which was a variation of U. I mean, so far it may look a little bit artificial because I didn't really connect completely everything with what the enthalpy is with what we can measure, but we'll get there. Now we have two more possibilities, right? Let's think about this from purely combinatorics approach. We have T, S, P, and V. So we already combined S and P and S and P and S and V. Now we can also combine T and P and T and V, right, as the natural variable. And it's exactly what we are going to do now. So the first one that we are going to do, we are going to go back to the internal energy, and just the same exercise as we did before by canceling PdV, you know, by adding PV to U. Now we want to cancel TDS. So clearly, to do that, if I subtract T times S from U, and I take the differential of U, I'm going to get two terms, minus TDS plus SDT, and of course that's going to get rid of TDS. So let's do that, and this is called the Helmholtz function, and we are going to see in the next few minutes how it's connected to work. Okay, so F is equal to U minus TS, so I hope I gave you the explanation why minus TS is there. It's not arbitrary at all. It's just because when I calculate dF, I can fairly easily see that I'm getting rid of this annoying term, which is TS, right? So instead now, the natural variable, which seems to be attractive to me, is temperature and volume. Temperature and volumes now start to be two variable, natural variable, that are much easier to control experimentally. Now, of course, we're going to consider some specific cases, like an isothermal process. Again, isothermal is constant temperature. I hope that's no surprise to anybody. Isobaric, constant pressure. Isochoric, constant volume. Adiabatic without heat exchange. Isothermal is constant temperature. And so we can write that, of course, constant temperature means that the dT is equal to 0, no variation in temperature. And we find that the differential dF is equal to minus PdV, which is, of course, shows that it's a state variable. And then that means that we can calculate the variation in Helmholtz function by the integral between two volumes. And we find, of course, something that looks very much like work, right? And remember that we introduced minus PdV, and I think this is something I insisted, but I'm going to insist it on again. Minus PdV is really only defined as the reversible work, right? The ones when we don't have to worry about shock waves, turbulence, or anything like that in the fluid. So that means now that it looks like the variation in the Helmholtz function is related to the change in work, in reversible work, between two volumes at constant temperature. Right? If I was not at constant temperature, I could not drop the minus SDT term. Good. So let's try to say a little bit more about this. As I said, F represents the reversible work. I like to insist on reversible work that done by the system on the surrounding. Can be positive or negative, just the same as before. The work is done on the system, which would be positive, or work done by the system, which in this case would be negative, just like we described before. So it looks, and we are going to discuss this in a few minutes, that in fact, F represents the maximum of work that we can get out of the system at constant temperature. Okay? We will discuss that. I mean, this is something that's going to come in handy in a few minutes. And of course, we can again use the properties of multivariable calculus, which means that the prefactor, you know, the one before dt, is the entropy. So the entropy will be simply given by minus the partial derivative of the Helmholtz function as a function of temperature at constant volume, of course, constant volume, because the other term should not change while we do this derivative. So that's already giving me, if I'm allowed to get access to the Helmholtz function, that's a good way to calculate the entropy, to measure the entropy, really, to calculate from a measurement. And then, of course, we can do the same for pressure using the same trick, and we find that the pressure can be obtained through an isothermal process by calculating the derivative of the Helmholtz free energy as a function of volume. I already said free energy. I actually kind of jumped the guns, but I will explain to you why I said free energy, even though I didn't explain what it was yet. Okay. So, of course, if we work at constant temperature and constant volume, so please understand here that we are introducing all those functions so that we can easily impose constraints, such as constant temperature and constant volume. We see that dF does not change, and F is therefore constant. So it's very important because it's basically a conserved property, and we like conserved property in physics, and this one, F, is the ideal choice for a case where we have isochoric and isothermal process. And of course, the last possibilities I have now is to try to yet again change the natural variable, and now I would like to have pressure, right? Remember, I always think about chemists preferring pressure to be the natural variable, so they want pressure, but they also want temperature, because in the lab this is something that we can control, temperature and pressure, instead of volume and entropy that we would have in internal energy. And so we come up with another function which is called the Gibbs function, and by now you shouldn't be surprised how it's obtained. We already got rid of the PDV and we replace it by a VDP in the Helmholtz, in the enthalpy. Sorry, the H is kind of a little bit confusing. H is not Helmholtz, it's the enthalpy. So we already got rid of that, but we still had a TdS term in the Helmholtz, so now we are going to remove TS, so that when we calculate the exact differential, we are going to get rid of the minus TdS, but instead we are going to introduce a SDT. Okay, so now that means that my differential dg, which is for the Gibbs function, the same Gibbs that we have met for the general definition of the entropy from a statistical standpoint, but for the using probabilities of the macrostate. I mean, this was one of the last topic we covered in the last lecture. And then we find that, of course, dg is equal to minus sdt plus vdp. We have, therefore, the natural variable temperature and pressure, just like we wanted. And again, same exercise as before, nothing new really. If we work at constant pressure and constant temperature, so an isobaric, an isothermal process, in such a process, dg is conserved. And again, we like conserved quantity, and this is the choice of function that we want to do if we use at constant isotherm and constant temperature and constant pressure. And this is interesting because, again, this is a new state variable, and it's only going to depend on the state itself, not the path to get to that point. Same way as before, we have yet again other ways to calculate the entropy and the volume, but in this case under different constraint. So if you were somebody asked you, can you calculate the entropy at using the Gibbs function, and you would say yes, so long as you can keep the pressure constant. That's the idea. That's how you should read those equations. How can you get the volume at constant temperature? Well, you get that by, for example, calculating the partial derivative of the Gibbs function as a function of pressure while keeping temperature constant. The signs there change, of course, because we have a mixture of plus and minus signs, simply because the du that we started from had TdS minus PDV, and the minus was needed there because work done on the systems. That means when the volume changes, has to be when the volume decreases, had to have the right sign. So it had to be positive because that's work done on the system. Okay, this is all where everything that we've studied so far comes in handy to understand what we're talking about. So this is the summary of everything we just discussed. I think the logical evolution for these is fairly straightforward. The big mistake you would make would be to try to remember all these things, to try to memorize all these things. Of course, remember them, but don't memorize them. I think the only thing you really need to know is is du is equal to TdS minus PDV. All the others can be rebuilt the way I told you. How do you get rid of TdS? How do you get rid of PV? And so you remember the enthalpy is really related to heat at constant pressure. So think about chemists doing the experiment at constant pressure and they get heat from enthalpy. Think about Gibbs as also the preferred way for chemists to know what is the work that you can calculate at constant pressure, and then the Helmholtz is the last one. So really it looks like a complicated table. It's not. All you really need to remember is the first one, is actually du equal TdS minus PdV, and all the rest can be rebuilt quite easily. Now we can use all those derivatives there. So the first derivative that's on the last two columns of this table are starting to give you a lot of information, ways to calculate temperature, entropy, pressure, volume, and so on and so forth, under different constraints. Again, I remind you, the constraint has a subscript in this derivative. That means that you can start to calculate a certain number of function now. And for example, we can calculate the internal energy and the enthalpy, and then we can relate the different functions with one another. So they are pretty much related. And you see, for example, the internal energy can be calculated from the first derivative of Helmholtz over temperature for constant volume. That's something you can do, and also calculate the enthalpy the same way, but starting from Gibbs. And you can prove that the following way. So first of all, you go in the table I showed you before, and you see the entropy is given by these there are two ways to calculate the entropy, either at constant volume or constant pressure, from the Helmholtz or from the Gibbs free energy again. And of course, if you remember we are interested in U. So U can be written as F plus Ts. Well, since F is equal to U minus Ts. Now, what's nice is that we know what S is. We know what S is as a constant volume. So U is going to be equal to F minus T dF over dt. And of course, people usually have no problem with chain rules for derivative. Sometimes they have more trouble going the reverse. But here, if your eye is trained with calculus, you see that F minus T dF over dt at constant volume is really the result of a chain rule, and the chain rule is simply the derivative of F over T as a function of T. Okay, so you can calculate this, and likewise you can calculate the enthalpy as well as a derivative of the Gibbs free energy divided by time. These equations are actually very useful, because that means that if you know two of them, you know the other two as well. And these are called the Gibbs-Helmholtz equation. So if you ever do chemical engineering or chemistry, these equations are very much used. Okay, so very good. So now I kind of motivated in fact, purely from a mathematical standpoint, why we want to introduce those equations, just to change the natural variable so that we have a handle on the actual experimental constraint. But so far you can scratch your head and say, well, all nice, but what really is enthalpy? What really is Gibbs function? What really is Helmholtz? What do they represent in reality? Yes, I can believe these are exact differential. I can believe there's a function of states. And I also understand that they are connected to all the other variables in the way we've done it. But isn't that all artificial? So that's the big question we can have. And in fact, I'm going to try to convince you now that they are not exactly artificial. They do represent measurable quantities depending on the type of constraint. So the idea of constraint already is pretty clear. The constraints are related to the natural variable that I want to have control over, so that I can do the ds or dt or dp or dv equal to 0. These are my constraints. So a constraint, for example, if somebody tells you, I'm going to do an isothermal isobaric experiment, and what are the constraints? Well, the constraints are pressure and temperature. That's really what it means. It's just a translation of the actual condition. So let's first talk about free energy. This idea of free energy means this is energy. This is not energy that comes for free. That's not what it means. Free energy is energy that can be used to do work. Okay, so this is a very important concept here. And consider, for example, somebody with a rock on top of a cliff and dropping the rock. As you know that at the beginning, when the rock is on top, there is the possibility of doing work of the mass is pretty large. Imagine that rock would be attached to some pulley or some other mechanical device, the fact that you drop it from the cliff, think about a waterfall, for example, means that there is that particular system is able to do work, right? And remember, doing work is exactly finding ways for a system, thermodynamical system, to do work is really kind of the holy grail of thermodynamics, like heat engine and so on and so forth, which were engines that are trying to transform heat into work, and with the constraint of the second law of thermodynamics. So the question is, let's go back to this. The question is, the internal energy does not tell me anything about what is the energy that's available to doing work. U is basically telling you, I'm going to take all sorts of different sources of energy, heat, work, I'm putting them together, and what I'm telling you is that that number is a constant, for example, when du equal to 0, or the total energy is conserved. Okay? But this is all good and nice, but in practice it's not very useful, because it's not telling me anything about what is actually the amount of that energy that can be used for work, which is really what we are interested in here. So the concept, the idea of the new state function is to answer that question. What is the actual work that can be done by a system? Not the total energy, that's not very useful, but instead, what is the energy that can do work, the potential of doing work? For example, this is exactly what happens with this rock on top of a cliff. There is from first year physics, that there is work, that the potential energy of that rock is going to be able to do work, and you know it. You know that is the way it functions here. So let's try to see how we can do this, and also what are the conditions under which the work can be done. What I mean by this is that, again, the constraint will actually affect the amount of work we can do. So let's try to talk about free energy a little bit more. So if you consider a system with a fixed volume, okay, and then we hold it at a constant temperature. So in other words, this is an isochoric, isothermal process. We know that the heat that enters the system is always going to be smaller or equal to TdS. Remember, this equation is actually an equation that I copied from a previous lecture where we defined the entropy. In fact, the sign larger or equal is actually coming straight from the Clausius theorem. So Clausius theorem, if you do not remember where this equation comes from, just refer back to the Clausius inequality. So, of course, by the first law, we can move du and dq around. Remember the notation for the dq and dw, because we don't have exact differential. So dq is equal to du minus dw. That means that because dq has to be smaller or equal to TdS, we find that the work added to the system, dw, is going to be larger or equal to du minus TdS. I mean, this simple manipulation here. Okay. I would like to insist that now on the right-hand side, we did not impose any reversibility, because this is the reason why we have an inequality instead of an equality. So we have an inequality instead of equality. Sorry. Okay. So since the temperature is going to be fixed, that was the constraint we started from on this slide. We know that it turns out that if I calculate df is exactly equal to Tu minus TdS. I mean, this is what we recalculate on this slide. So basically, df, so the change in Helmholtz energy, is du minus Ts, which is exactly what shows up on the right-hand side of the equation in the middle of the slide. Therefore, dw is larger or equal to df. So the amount of work that I add to the amount of work that we can do on a system is always larger or equal to the change in Helmholtz energy. So let me tell you a little bit more. So doing work on a system increases the system's Helmholtz function. which of course I already kind of gave it spoiler before. There's a reason why we call the Helmholtz function really the Helmholtz free energy. So before I may have mentioned free energy for Helmholtz. We didn't know that. Now we know thanks to this equation. So the Helmholtz free energy is this function that actually increases up to dW when we do work on the system. Okay. In fact, when I say up to dW, it's going to be an equality. It's going to be equal to dW when the work is done in a reversible process. Remember, this inequality comes from Clausius, which becomes an equality for a reversible process. So that means that the free energy, the Helmholtz free energy, the change in Helmholtz free energy will be directly connected to the amount of work that can be done or that can be added to the system. Okay, that's the reason why it's such an important function, because it gives me a handle on this useful energy, if you will. Okay, so now if you think about this process that we started from with the pebble on top of the cliff. Now the pebble fell and on the bottom of the cliff. Now you are actually going to take the pebble and bring it back up by one means or another. The fact that you are doing this, you're actually adding potential of the system to do work, because by bringing it from the bottom to the top, you're actually changing the Helmholtz free energy by the amount of work that pebble will be able to perform later if you drop it back and pull a pulley or something like this. So the internal energy, of course, is going to change as well, but it's not going to tell you anything about the capacity of the system to do work. The Helmholtz free energy will do that. At least remember what we did on the previous slide, and I'm going to backtrack a little bit to here. So long as we work at fixed volume and constant temperature. I like to insist on that. Okay, nice. All right. So another example that's coming from the book, and I think it's very interesting, is oil. I mean, everything that we burn to do work, right? For example, we do in the Otto cycle to the heat engine, right? So what we are interested in, for example, when we look at a substance like oil or anything that we want to burn, what matters is really the free energy. How much work can I do with a given substance? I'm not interested in how much heat it produces necessarily. What I want to know is how much work it can do, and this can be we access this with the Helmholtz function. Now you can say, well, hold on a second. What happens? You always give all those constraints. It looks very sometimes pretty harsh constraint, like constant volume, constant temperature. But most of the time, I want to do this at constant pressure. And of course, by now, I hope that you understood where we're going with this. If you want to change the constraint, well, you have to change the function we use. So instead of using constant volume, which would be for Helmholtz, we want to use constant pressure, will be for Gibbs. And this is exactly what we will do. So Gibbs becomes the function we want to use to get the amount of free energy, so energy that can be used to do work at constant pressure. Okay, nice. So now here is something that's quite interesting. If you remember, dF was smaller or equal to dW. In all generality, the work didn't have to be reversible. It would only be equal if the work was reversible. I just like to insist on this. So imagine now that your system is mechanically isolated. In other words, no work can be done on the system or can be extracted from the system. In other words, dW equal to 0, right? And so in that case, dF, of course, is smaller or equal to dW, which is equal to 0. Therefore, dF is always negative. Okay. So that's good, because that means that if I take any system, okay, any changes, I mean, it's good. I don't know if it's good, but it's useful to understanding what's the dynamics of a system going to equilibrium, is that a system, if you take any system that's mechanically isolated from the surrounding, okay, and I repeat, mechanically isolated means that no work can be done on the system, and the system can't do any work on the surrounding. If you take such a system, it's going to, any changes to the system will lead to a decrease in the Helmholtz free energy. So df has to be equal to smaller or equal to 0. And if the process we do are reversible, that there is no decrease. So you see a little bit the idea already now that we are touching a point of interest. If I do not a reversible process, I lose capacity for the system to do work. Even if I don't do work, even if the system doesn't do any work. Okay? So think about those inequality again. The mathematics is very, very straightforward, but the interpretation and the concept are a little bit more subtle sometimes. So df has to be negative, so that means that if you leave your system that's mechanically isolated to its own devices, it's going to go so that it's going to evolve so that the system free energy, Helmholtz free energy, is going to go down. There is no other way. There is no going up so long as it is mechanically isolated. Of course, it can go positive if it's not mechanically isolated, but it is mechanically isolated in this example. So how is it going to keep going down, right? Until what? Well, until it achieves a minimum. So in other words, such a system that's mechanically isolated will, which is a constraint, right, is going to evolve so as to minimize the Helmholtz free energy. So you see that's crucial. That's crucial because this function now, it really represents a physical, as a very strong physical interpretation. This is the function that's going to be minimized at equilibrium for a system that's mechanically isolated. Okay? Very good. But of course, we have other constraints that we can apply. So other constraint, for example, is constant temperature, constant pressure. So that's what is shown on the little cartoon on the right-hand side there. Basically, the entire system there is, we have the system inside with the white box that's surrounded by a heat bath and a constant pressure system. So T and P, T0 and P0 are held constant. So these are different constraints than what I had before. Well, that means that we can try to see where we go with this. Okay, so now we are not talking about heat here. I mean, we don't have a constraint on heat. So basically, if we don't have a constraint on heat, that's what we have to look at. And once again, we can calculate the change in entropy. So of the system at temperature T0, that's what the system is. So T0 ds will be larger or equal to dq, just the same way as we did 2 slides ago from the definition of entropy and the inequality coming from the Clausius inequality. And of course, in that case, we find that dq can be connected to the internal energy. So now here, this is something that can look a little bit artificial, so I need to spend a minute. In the equation there, dq equal to du minus dw minus p0 dv, we essentially have separated the amount of work. We have separated the work in 2 terms. So the dw, which is the usual work that we are talking about, and the other term, p0 dv, is essentially the work done by the system itself, so the white box, to increase its volume against the pressure P0 of the surrounding. So basically, we are separating, and this is an important concept. We are separating the usual work that we do here to the work that the system has to do to increase, to make space, to make room, or to reduce. Okay, so the work the system has to do to basically keep its pressure constant, if you will, right? Keep its pressure constant is minus P0 dV. So we separate that term. It's fine so long as we know what we are talking about, and that's good. So now let's try to look at this equation, and I'm going to replace dq by T0 ds. I mean, at least I'm going to say that dq has to be smaller or equal to T0 ds, and rearrange the term. So bear with me. Imagine that equation there, dq is equal to du minus dw minus p0 dv. And you say that equation has to be smaller or equal to T0 ds, and rearrange the whole thing. So do this in your mind. You will see that dw will be larger or equal to du plus p0 dv minus T0 ds. If you didn't follow me, that's fine, because the equation is on the next slide. So in order to get this equation, I use what I had before, with the inequality coming from the fact that I replaced dq by T0 ds. Well, I didn't replace, I just had an inequality between them. Okay, so basically what this equation tells me is that the amount of work that the system can do, and I made sure to subtract the work that the system has to do to keep its pressure constant. Okay, that's the P0 dV on the right hand side. So the amount of work that the system can do is larger or equal to du plus P0 dV minus T0 ds. And we can now define a new function, and I should probably have put this in red and boldface because it's an important definition, but I didn't, is that the availability A is defined as U plus P0V minus T0S. Now, of course, we can calculate the differential of A, which is du minus all the other terms. Some terms will drop, especially the V dP, since P is a constant, and as well as S dt, since temperature is a constant. Okay, so clearly we get directly this term there. And then we find that this function that we've defined, the availability function there, shows in other generality, in generality of in other constraints, sorry, of temperature and pressure, that the amount of work that can be done by the system is bounded, if you will, by the change in availability. Okay, so the availability function is given there in all generality, and we are going to see what it is in different cases in just a minute. So the amount of work, again, under those conditions, is bounded, if you will, by the change in availability function. So availability function is a function that gives you really information about the amount of free energy, so amount of work that the system can do. And the equality, of course, again, will be there for a reversible system. Remember that all the inequality here always comes from Clausius inequality, so it's a good idea to review this if you forgot. So just to summarize the discussion I just had, the changes in availability provides the free energy available to doing work. So we work first with a specific case of a fixed volume and temperature. That's what we did when we introduced because there is a natural variable for the Helmholtz free energy. But if the system is mechanically isolated, we can use dA smaller or equal to 0. Okay. What's nice about this is that the second law of thermodynamics is automatically included, and I know I insist on this a lot, but the Clausius inequality is another equivalent statement of the second law of thermodynamics. So the fact that it shows up in these equations shows that you are sure that to obey the second law of thermodynamics, of course the first law as well, which is kind of reassuring when you do thermodynamics to make sure you obey the fundamental laws. So let's say a little bit more about the constraint. Okay, we just introduced a function a, which I'm going to reintroduce at the top of this slide here. And so let's go back to see a little bit what we meant, what we mean by the consequences of imposing that the change in availability. So suppose that you have a thermally isolated system at fixed volume. Well, you already know what it means. A thermally isolated system with fixed volume means that the internal energy will be equal to 0, since no heat can come in and out, and the work can't do any work on the outside. So du has to be equal to 0 in all generality. And so that means that the derivative, the differential of A, is going to simplify it quite a bit. Because all the derivative corresponding to u, p, v, and t are going to drop since they're all constants, and that means that the only remaining derivative is ds. So dA will be equal to minus t0 ds. We showed in all generality that dA had to be smaller or equal to 0, again coming from Clausius inequality, and so in this case, because minus t0 is always a negative number, sorry. That means that this change in availability translates into the fact that the change in entropy have to be positive or equal to 0 for a reversible situation. So that means that the system, any changes in a system that's thermally isolated and has fixed volume, any changes will lead to an increase in entropy, and so that you minimize the availability. So you have to think about this in a way that if any processes will decrease the capacity of a system to do work, and this is translated to the fact that the entropy is increasing. So finally, we are starting to really make all those connections between the different types of energy, and I think that's very important. Now, this is one constraint, and I hope by now you understood how we do the constraint. We start with a fairly complicated function like A, and then when we take the differential, we get a lot of variations, but then we impose a number of constraints that drops a lot of those differential. That's always the same thing, and so therefore you have kind of a general principle which becomes specific depending on the constraint you have. So for example, if we work with fixed volume and constant temperature, just like we did a few minutes ago for the Helmholtz free energy, let's see if we get the same result. Well, of course, spoiler alert again, we are going to get the same result. If we take the differential of A at constant volume and temperature, we are going to drop a number of terms. The only one that are left is du minus T0 ds, which has to be smaller or equal to 0. Remember, we proved that. We did prove that in all generality using Clausius inequality. And then what we see is that, of course, du minus T0 ds is nothing else than dF, which is the Helmholtz free energy. So in other words, in this case, at fixed volume at constant temperature, the change in availability is the same as the change in Helmholtz free energy. And we know this is smaller or equal to 0. And again, the equilibrium state will be the one that minimizes F. Sometimes it's confusing to students. How can I conclude that it's minimizing F? Well, because the F is negative, right? So any changes is going to be negative, is going to bring the function down until nothing changes. And when nothing changes, that means that dF is equal to 0. By the way, nothing changing is a reversible process. Okay, so nothing is really violated here. Very nice. Okay, let's keep going. And now, of course, the one that you've all waited for a long time. What happens at constant pressure and temperature? And if you followed up to now, you know, wow, that's going to be something related probably with Gibbs free energy, maybe? Yes, of course, that's what it is. And so we do the exact same exercise. In this case, the actual shape of dA is going to be slightly different because we are working at constant pressure and temperature. And so we can manipulate a little bit dg. dg is going to be equal to, in fact, dA under these conditions. And I'm not going to linger too much on this. I mean, you can pause this screencast and convince yourself of the math. It's the same as we had before. Again, with the constraint of dP equals dt equals 0, because these are isobaric and isothermal processes. And again, the change in availability function, that's again reminded at the top of this slide, under these particular constraints, and I like to insist on this, under this particular constraint is equal to the change in changes in Gibbs free energy, which has to be smaller or equal to 0. So again, if you work under constant pressure and temperature, any processes that will lead to a reduction of the Gibbs free energy until you get into equilibrium. So in other words, the equilibrium state corresponds to the minimum of the Gibbs free energy at constant pressure and temperature. So you see, all these things that look complicated are actually not complicated at all. They are basically telling you how things change under different constraints. Most of the time, you have to play between Helmholtz free energy and Gibbs free energy, depending if you work at constant volume and constant temperature, constant pressure, sorry, and also constant temperature of course, in both cases. But the Gibbs free energy is really the one that's used mostly in most chemical reaction, unless you work in a closed vessel, of course, in which case the Helmholtz free energy is the one you want to use. Okay, so another example is from chemistry, is that you've been told that what really matters to see if a system is going to react is to look at the change in the heat that's released. Okay, so we already know how to calculate this now, because if we, again, chemical reaction, I'm not going to say that again, mostly working under constant pressure, and the right thing to look at constant pressure is either the enthalpy or the Gibbs free energy. If you are more interested in the work you're going to do in the Gibbs, if you're more interested into the heat, you're going to look at the enthalpy. So the heat of reaction, of course, is going to be obtained from a change in enthalpy. You can convince yourself by going back into the DH. Okay, so delta H is going to be equal to delta Q for reversible process. Remember that the TdS is equal to delta Q only if it's a reversible process. I can't repeat this enough. So basically, if you have a reversible process, the change in enthalpy is going to give you the amount of heat that's transferred in or out of the reaction. Okay, so if you find that the enthalpy is going down, the system is exothermic, and if the enthalpy is going up, the system is endothermic. However, the problem with this is this does not quite tell you the whole story, because this is not these equations are not necessarily based on this principle of the availability going down. So for that, we actually need to calculate which way the availability function how it changes. And we know that for this system to happen spontaneously, dA has to go down, has to be negative. We just spent the last 15 minutes on this. So so we have to calculate delta G, basically, okay? And delta G has to be negative. And of course, we can calculate delta G depending on this. And of course, delta G can be calculated at constant temperature and constant pressure. And so we can relate delta G and delta H and so on and so forth. Okay, so that's the way, that's why we use those state functions, and I think that they are extremely important for actual thermodynamics. Well, as opposed to theoretical thermodynamics. Okay, so as I already told you before, we have a slew of different partial derivatives. Clearly, they must be related to one another. I mean, there are so many of them that we can't have more equations that we have unknowns, right? So that means that they are related to one another, and in fact, that's true. And the formal relationship between them is called the Maxwell's relations. Again, Maxwell's relation looks like complicated, but it's not. It's just an application of a simple property of exact differential. So if you have the exact differential df that you have shown here in the middle of the slide, you know the coefficients df over dx at constant y and df over dy constant x. You can show by using the Stokes theorem, and I invite you to review this in the appendix of the Blundell and Blundell book. That's all proven and clearly shown that if it's an exact differential, then that means that the circulation, in other words, the integration over a closed loop, has to be equal to 0, and therefore you have access to the second derivative there. And in fact, the cross derivative, so df over dx dy or df over dy dx, if you have an exact differential, these are equal. Okay, these are equal, and therefore that allows me to make connections between the first derivative, basically, that is going to be equal. And so this is where the Maxwell relations are based off this fundamental properties of exact differential. So I'm not going to describe them all for you. I'm just going to show you how it works, okay? Because again, this is something that you can rebuild from scratch without cluttering your central memory system too much. Okay, So, for example, let's use the Gibbs free energy, and we know that the variation in the Gibbs free energy is minus SdT plus VdP. Remember, Gibbs is natural variable temperature and pressure. Good, we remember that. Then the first equation I had, the equation there for the exact differential dg, can also be written from a mathematical standpoint. And that means that allows me to get a definition of the entropy and a definition of the volume. We've seen this before, but I'd like to remind you of this. Now we know, because it's an exact differential, that that we have the cross derivative are also correct. So that means that if I do a derivative of the entropy with respect to pressure, but at constant temperature, that's going to be equal to the derivative of the volume with respect to temperature at constant pressure, right? So this is basically everything that's written on this slide. So you see, you have those nice relations between the entropy and the volume. So these are actually relationships that exist because we have exact differentials. So this is all purely mathematical. There is absolutely no physics in here at this point. It's just a matter of remembering that we have exact differential and we have a function of state. And of course, we have I could write one such a slide for each of the function of state I introduced. So one for U, one for H, one for F, and one for G. That means that there will be 4 relationship, Maxwell relation, like the one that's shown here. So the last equation on this slide, it's a Maxwell relation. So we can just put all the Maxwell relation in one box, and they are here. And that gives me a connection between the different derivative of the variable of state. Again, these are very convenient when we are trying to solve actual problem in thermodynamics. And this is where students usually have a long sigh and say, that's not for me. Well, frankly, this is purely mechanical. This is the kind of problem that if you had a powerful symbolic coding, I mean, you could do that in Mathematica or another software like this. They could be able to solve all this directly without adding any new physical intuition. So this is purely mechanical here. Of course, you need to know how to do it, but you certainly do not need to memorize everything here. So let me show you a couple of examples of how we do this, how these relationships are useful. So for example, this is something that we can calculate. How do we change the specific heat? How does the specific heat at constant pressure changes with pressure for fixed temperature, and how the same for the specific heat at constant volume? So these are things that we can calculate, and so this is almost like a detective work more than anything else. It's like a puzzle. How can we bring all the pieces together? So these are good exercises to do. These are useful for people who want to be strong in thermodynamics, but this is certainly not a necessary condition to be strong in thermodynamics, where the concept, in my opinion, are much harder to understand than the math that we are going to show. But I'm going to explain it nonetheless because it's very important, obviously. So first of all, we start with the definition of the heat capacity at constant volume, and we've seen those before, right? We know that those definitions have been derived before. So now you see that things that we need to calculate are variation of entropy with respect to temperature, and then also entropy with respect to temperature at constant pressure or constant volume. Okay, so we are only going to do one of the two equations, and the other one follows the same steps. So the first equation there, of course, is that we can replace we take the derivative with respect to pressure at constant temperature of Cp from the definition. And there we have to use a chain rule for the derivatives. And so we end up, essentially what we do, we end up with the derivative of the entropy with respect to pressure at constant temperature. But that we know, we've seen this before. This is related by Maxwell's equation. This is related to the derivative of volume with respect to temperature at constant pressure. Okay, so and that means that we get a second derivative of the volume with respect to temperature. So you see here that that we can obtain. I mean, this is pretty striking. The amount of heat that you need to the variation of the amount of heat you need to increase the temperature of a body by 1 Kelvin at constant pressure. So that derivative, you can obtain it by simply measuring the changes in volume as a function of temperature at constant pressure. So that's what this equation means. So you see, by relating all those equations, all those variables of states together, we can have access to numbers that look impossible to calculate, and we can relate them to ones that are directly measurable, like volume and temperature. So this is something that's very often true in thermodynamics, because all the variables are connected to one another through Maxwell's equation. For example, Maxwell's relation. We don't usually say Maxwell's equation to avoid confusing with electromagnetic theory. But the point is, we can relate all this. It's almost the magic of thermodynamics, and of course we can also do that for the volume. So I'd like to attract you to attract your attention. Sorry, on something. For example, suppose that you have an ideal gas. Remember, Cp and Cv were constant. So and then we see, of course, that we see that's of course the case. And so we understand, for example, the second derivative of the volume with respect to temperature. If you remember the ideal gas law, it's going to be equal to 0, because PV equal KT, or PV equal RT. That means that it's a linear term, so the second derivative has to be equal to 0. There is no curvature. So for the ideal gas, Cp and Cv indeed do not change with respect to pressure and volume, as we have seen. So how do you solve a problem like this? How do you know how to go from this? Well, there are some recipes, and also there is some patience to do this. And but there is a general procedure that I'm going to show you, and these are the things these are basically the dictionaries where you have to go in order to solve problem. The first of all, you have to make sure that you write your thermodynamic potentials in terms of the variable that matter. So if somebody wants to work with constant pressure and constant temperature, clearly the potential you want to use is Gibbs. If you want to work at constant entropy and constant volume, you would use the internal energy. These kind of things. So these are all things that come from the definition of the potential. So that's fairly easy. Second, you remember all the math that we've seen. Okay, so I'm just going to get there in a second. You also have to remember the Maxwell's relation. So this is the 4 equations I showed you. Should be on a piece of paper somewhere. It's almost like crib sheets have been invented for thermodynamics, for students taking thermodynamics. You have to, the Maxwell's relation can be manipulated, inverted, and work with them by using a number of theorems from multivariable calculus. The first one is the reciprocity theorem. This is the top one on the green box. The second one is the reciprocal theorem, and when you combine them both, you can have the last derivative there. So a mistake that students make very often is that they forget the minus sign. And so this is not a trivial thing. It is, and I can't insist enough on this. The reason why this is not a trivial equation, the last one, is because the 2 partial derivatives on the right-hand side are done under different constraints. If they were done under the same constraint, like say y or so, you could actually simplify, if you will, the fraction. But you cannot, I mean, when I say simplify, it's basically using the first equation on reciprocal theorem. The point is that be very careful when you do those changes. There is no shortcuts to rigor when you do this. And so you do all that, you do all those things, and then you end up with a number of derivatives. And you are not, it's not really helping until you connect them to some definition, so more definitions, I would say. For example, the heat capacity, just like we did in the previous example, are defined. These are numbers that are defined with respect to some known function of state, like entropy and temperature. And again, you have a list of those equations somewhere. And then this is not enough, okay? This is CV and CP are useful, but it's not enough. There are also other derivatives that are defined as numbers if you will, in tables and reference tables, and we call them the general susceptibility. So I'm going to talk for a few minutes about susceptibility, which are essentially pure definition of things that can be measured. We are going a little bit away from thermodynamics and more into definition, of a lexicon of definition. So a susceptibility is essentially, a general susceptibility is essentially a variation of a particular variable with respect to a constraint that's imposed, with respect to an external force, as we could call it, general force. For example, how does the volume changes when we change temperature at constant, let's say, pressure or something like that, right? So this would be an example. And so these answer questions that we could ask ourselves. So instead of going into being too formal, let me show you some example here. Thermal expansivity are two examples. Expansivity, as you would expect, expansive means that that you increase the volume, and so you increase the volume with a function of temperature. So the fact that you are heating up, I mean, you increase the temperature of a body, you're heating it up, you change the volume, right? But you can do that under different constraints. You can do that under constant pressure, okay? Or you can do that, for example, under constant entropy, or without any exchange in heat. That would be an adiabatic expansivity. So these are explained here. The 1 over V come from the fact that we have the relative change, so that you have a so that the actual volume you start from is basically normalized. Okay, but these are definitions, really. These are definitions that you use, that you have somewhere, that essentially to help you simplify the notations. Okay. You also have the compressibility. Compressibility will be the change in volume, no longer as a function of temperature, but as a function of pressure. So when you push on a system, when you impose pressure on a system, how does the volume changes? Well, again, it's going to change depending if you are adiabatic or if you are isothermal. And this is the equation. And again, we talk about fractional change. So we have 1 over the volumes to make sure that because otherwise, if you have a larger volume, of course, we will have a larger derivative, which makes little sense. So that's the reason why we normalize. The negative signs are there because we want those numbers to be positive in general, because the volume is usually going to decrease when you increase the pressure. So dV over dt is going to be a negative number. So since we like those compressibility to be positive, we put a negative sign. If you remember the expansivity, that was different. If you increase the temperature, the volume usually we're going to increase, so dV over dt is going to be a positive number, so no need for negative sign. Okay. So let's try to show this in 3 examples here. Bear with me. This is essentially, as I said, like trying to solve a 5,000 piece puzzle, and you have all the list of puzzle and you have to put them together. This is mostly a work of patience and almost a detective work. So let's try to see this, okay? So do not worry about what I put on the right-hand side. These are all the equations that are going to come in handy for this. So just to show you an example of what you need, the kind of dictionary I'm talking about. So consider the entropy depending on, of course, temperature and volume, and show that Cp minus Cv is equal to what's written there, okay? First of all, we start. When somebody tells you consider S equal S of T of V, you usually going to write ds is the differential of S, just like written there, and you're going to try to replace those by what you know. And we are going to kind of use whatever I have on the right hand side there that I have from getting into the Maxwell equation, Maxwell relation, reciprocity, reciprocal heat capacity, and the definition of compressibility and expansivity. So first of all, we can rewrite this by taking the derivative with respect to the temperature as at constant pressure. Okay, so that's what we do. So you see how you get from the first line to the line right below the arrow is by taking the derivative with respect to temperature with constant pressure. So we have this. The reason why we do this is because we wanted to show a ds over dt and a ds over dt at either constant volume or constant pressure, because we know these are CV and CP, right? These are shown the definition on top right. And you see the definition of CV and CP in there, so you can already simplify CV and CP. And then the manipulation there, this is the arrow that is long, there's a couple of steps, which are simply about identifying the ds over dv. This is something that we need, ds over dv at constant temperature, and then you use Maxwell relation to relate it to pressure, and it's exactly what's done here. I invite you to pause the screencast at this point and convince yourself that you can do this. Again, this is mostly about plugging the numbers and making sure you remember your basic and fundamental differential equation and differential properties like reciprocity, reciprocal, and that kind of things. So let's try to have a couple of more examples, maybe in more details. So the first one I'm going to talk about is the entropy of 1 mole of the ideal gas. This is a problem we actually already encountered in the last lecture. Remember, we were working at constant temperature, and then we found that the change in entropy when the volume was doubling from V0 to V0, we found it was R ln 2. That was true for an ideal gas, and we proved that both using the statistical description of the entropy and the thermodynamic description of the entropy, if you remember. So let's try to see if we can show that in all generality. So again, we talk about entropy, so it looks to me like it's pretty obvious what we need to use here. Again, the ds over dt and ds over dt can be replaced by the definition of Cv over T. We were able to replace ds over dv at constant temperature by dp over dt at constant volume. Again, how did we do that? Well, we did that by using one of the Maxwell relation. And then now we have to calculate the derivative of the pressure with respect to temperature. But we remember that we have an ideal gas, and then the ideal gas PV equal RT. Therefore, dP over dt is R over V. Again, we'll replace this in the equation, and then we can then integrate the equation that we obtained, right? So the step that I didn't write there is Cv over T dt plus R over V dV. I integrate on both the left and the right, and of course we are quite happy there because we recognize integral that are fundamental integral. If we remember, Cv and R are constant. R is a constant, obviously. Cv is actually a constant, does not change with respect to temperature. The Cv does not change with temperature for an ideal gas, remember. So that means that when I integrate this, I get that the entropy for 1 mole of ideal gas is Cv ln T plus R ln V plus a constant, right? Because we cannot, there is always a constant in those indefinite integrals. Which is nice, because that means that the delta S, for example, if the temperature is constant for an isotherm process, and let's say the volume doubles, we see indeed that delta S is R ln the 2, just like we saw before. But here this equation is more general for a mole of ideal gas. So you see the process we've used here is really using Maxwell's equation and then remembering the properties we have for a mole of ideal gas. This is an example that you should really be able to solve without being led one by one. And again, do not focus on memorizing the equations. This is imagine that you have a list of equations on the right hand side and think that it's a very complicated puzzle, and then you have to put all the pieces together. This is really what it's all about. I'm going to do one more example here, which is the ratio of the isothermal and adiabatic compressibility which of course are this. I just defined them a couple of minutes ago, and by definitions they are here. There's nothing new here. It's definition. That's one of those pieces of the puzzle that's there. When you do a puzzle, you do not have to make the pieces each time, right? The pieces are given to you. This is, and even though you are supposed to be able to make the piece at some point, that's what we describe in this screencast. So let's keep moving. We want to replace. We want to play a little bit with those derivatives. So let's first consider this derivative here, and we know this derivative will be able to be replaced by this one. Okay, so remember I showed that in a yellow box a couple of slides ago. The negative signs come from the fact that we are doing derivatives at different constraints. So remember this. So how do I know that I have to do this here? Well, because we try different things and then we end up with what we want, because we are trying to connect this to other definition of CV, CP, and all sort of things like this. So that's what we do. Okay, so that's what we get, and we do also reciprocity theorem on the bottom, on the denominator. Okay, now we can impose the reciprocal theorem. The reciprocal theorem allows me to replace, to basically move dV over ds at constant pressure from the denominator over ds over dV at constant pressure in the numerator. Okay, this is the reciprocal theorem. Again, this is a formal procedure. It's not just, oh, these are fractions and I can just move them around. Okay, so all right, so just to explain to you how we got these are the terms that I just moved around. Okay, now we can also, we see that the derivative on the top, on the numerator and denominator now are all under the same constraint. So therefore, it is okay to so-called simplify the dV, because they are all calculated under the same constraint of pressure or volume on the bottom. So we also have this here. So that allows me to really simplify everything, and I end up with this. Now what's nice about this, of course, is that the change of entropy with respect to temperature and at constant pressure or volume are related to the heat capacity at constant pressure and constant volume. We've used that 3 times in this lecture already, and we end up with this. And of course, Cp over Cv is, as you remember, the adiabatic index. So we saw that the adiabatic index, which is Cp over Cv, is also the ratio between the isothermal and adiabatic compressibility. So that's very good, because that means that we can measure this adiabatic index can be calculated, can be measured different ways. So this concludes this chapter. I'm going to try to summarize what we've done today. We started from the thermodynamic potential. We started with U, and U has a good interpretation in terms of the total energy of the system. Problem with the U is that it's not a very convenient function of state, because it depends on the natural variable are S and V, which means that its U is only relevant for a process where I can control the entropy and the volume, which is not usually the case. So there I would just look at the math, and I said maybe I can modify U so that I can change which are the natural variable. And of course we have 4 natural variables we work with, which is temperature, entropy, pressure, and volume, which means that we end up with 4 we end up with different ways, as I put here, different way to combine them, just 4 ways to combine them, as shown here. And we introduce the internal energy, the enthalpy, the free energy, the Helmholtz free energy, and the Gibbs free energy. Realize that the free energy name came from the fact that they represent the maximum amount of work the system can make under certain constraints. For example, and the constraint will be will be, for example, for the Gibbs free energy, that will be the maximum amount of work that the system can do at constant temperature, at constant pressure. And we have the same for Helmholtz, but here in that case, the constraints are different. It's constant temperature and constant volume. And all this should come very clear by looking at the mathematical shape. We also realized that depending on the constraint, the system will lead to an equilibrium state that will, of course, obey those constraints. So, for example, under constant temperature and pressure, a system will lead to an equilibrium state that corresponds to a minimal Gibbs free energy. If you have constant temperature, constant volume, the system will tend to minimize the total Helmholtz free energy F, and so on and so forth. So this is really the idea that we are doing. For example, DH at constant pressure would correspond to the reversible heat that you can get in that system. So again, this is again in or out of that system. So enthalpy H will be related to the transfer of heat at constant pressure. So all these things are just about not doing math mechanically, but trying to understand what you're doing. And so this was generalized by introducing the availability function A, which is U plus PV0V minus T0S. And we introduced this essentially to generalize everything we've done so far, so that the differential dA, we show it was always negative. It's related to the second law of thermodynamics by translating Clausius inequality. And we found that this dA, so the change in availability, even tries to minimize the availability, okay? And that dA takes a different form depending if you are working with at constant pressure, constant volume, constant temperature, constant entropy, okay? And so that means that you are going to minimize a different function depending on those constraints, okay? So that's basically the idea. And so we've seen that in reality, thermodynamics tells you that you have to minimize a different one of those state functions depending on the constraint. It's basically what it is. So it's extremely convenient. So one thing I didn't put in this summary is that we also studied the Maxwell relations, and we introduced a number of definitions. And those definitions are really there because they correspond, like the expansivity or the compressibility, they do correspond to measurable quantities. And those measurable quantities, through the use of Maxwell relations and the definition and also property of exact differential, allow you to connect thermodynamics properties that look completely different, like heat and change in volume, for example, that kind of thing. Or also access to changes in entropy, which are not easy to measure, but we have a proxy, if you will. It's like getting a different equation that seemingly can seem completely disconnected at first sight, but actually completely formally connected through the Maxwell equation, Maxwell relation, sorry, and of course the fact that we have an exact differential. So this is one lecture which doesn't have to be complicated. There are lots of definitions, but I think I hope I managed to show you that it's extremely logical. And do not let the issue with novelty of definitions and lots of mathematical description, don't let it blind you in your understanding of why we do it, why we do this. And imagine when you review this lecture, when you study this, that you are allowed a piece of paper with 10 equations on them. And imagine which 10 equations you would put on. And you will realize those 10 equations are enough to basically not rely on your memory, but instead rely on your understanding of the material. So thank you. We will conclude this lecture here. And the next few lectures will allow us to conclude this part on the thermodynamics part, and then we will be able to move into the statistical mechanics part fully. Thank you.